Okay, so now in this example, we're going to use the same matrix and eigenvalues we saw in the previous example. So we have this matrix with its three distinct eigenvalues. So again, from the corollary, we know that this matrix is diagonalizable. Okay, because remember, if we have an n by n matrix with n distinct eigenvalues, then that matrix is diagonalizable. Okay, so now again, so these are the associated eigenvectors, but these also, again, remember, make up a basis. So this is going to be basis B. We'll call this basis B, and that's going to equal beta 1, beta 2, oops, and beta 3. Oops, don't want the curly braces. Like so. Okay, now the arrow diagram here gives this, right? So again, going back to this arrow diagram, gives us this, that D, the basis D, okay, is equal to P inverse TP, which is given by this here, right? So again, we can find the P using what we've learned, the techniques that we've learned before. So here's our P, okay? And so here's inverse of P. And so when we compose this, we get our D, which is diagonal. Okay? So again, it's diagonalizable. Now the bottom line of the diagram has this. So the bottom line here has this. So it takes the T of beta 1 and equals 1 times the beta 1 vector, etc. Okay? And so the action on the basis is going to be this. So the action on the basis is going to be sending them all to the 0 vector. Oops. Keep forgetting my arrows. Okay. Now here's how the top line of the arrow diagram represents the first of those three actions. So we're going to take this down here. Okay. So the top line represents this action here. So T minus 1 times I times beta 1 equals 0. And so we end up with this matrix equation. Now, of course, the representation of beta 1 with respect to the standard basis is itself. Now, to wrap everything up, to end this section observes that some matrices are similar to a diagonal matrix. The idea of eigenvalues arose as the entries of that diagonal matrix, although the definition applies more broadly than just to diagonalizable matrices. To find eigenvalues, we defined the characteristic equation that led to the final result, a criterion for diagonalizability. While it is useful for the theory, note that in application, finding eigenvalues this way is typically impractical. For one thing, the matrix may be large, and finding roots of a large degree polynomial is difficult. Okay, and that wraps up this subsection on eigenvalues and eigenvectors.